Hi and good evening. My name is Abdulaziz Hamid. I'm from Yemen. My matric number is 186529.
And my name is Muhammad Ishamuddin bin Muhammad Aris. My matric number is 181825 and I'm from Malaysia.
Hi, my name is Zhang Da. My matric number is 186479. I come from China.
So we are going to present about energy band diagrams of metal and semiconductors. So let's enjoy it. Hello, now I will explain about valence band, conduction band and forbidden energy gap. So here the basic of the energy band diagram. So as you can see there, the energy axis located at the y-axis and the valence electrons are at the valence band, which is have the highest energy. So usually valence band have partially or completely filled with the electron. So electron can move freely from valence band to the higher band to have some function. So the band here, the electron that we call it as the free electrons. The free electrons function to conduct electricity in the conductor, so we call it as a conduction of electron. So that's why we call the band as a conduction band. Okay, so usually conduction band have empty or partially filled with the electron. So the gap between the conduction band and valence band is called forbidden energy gap, or we can call it as energy band gap. Okay, so if the valence band
Now we are going to talk about the energy band diagrams for three types of materials that we have, and these three types of materials in every electronic device, they are conductors, insulators and semiconductors. In conductors, we would say that the electric current flows smoothly through that because it conducts the electric current. And insulators, they persist like a resistance to the electric current and does not make electricity flow through it. Semiconductors have both properties of conductors and insulators. To visualize this in a good manner, we're going to show you some bands, and this energy bands for the three materials: conduction band, insulator band, and also for the semiconductor band. And from here we would say that the bands that we see over here is this one. The first upper one is made of crystalline material for the semiconductor component inside, and at this crystalline part we talk about firstly about the conduction one. The conduction part, as we see in this video, the bonds in the valence band, in the down part, which is the valence band, is tightly bound together, but for the upper part, which is for the conductors, is really overlapping. This allows occupied by many conduction electrons, causing metal to become good electric current in conductors. Secondly, we would go for energy band of insulators. In the insulator, we have the conduction band, the valence band, and a gap between them. This gap is called the forbidden gap, and this the valence in this energy band, the valence band is filled with electrons, and the conduction band is empty. Because the valence band, the electrons is tightly bounded to the atoms. Electrons are unable to gain enough energy to move from the valence band to the conduction band. Now we will go to the third energy band, which is the insulator. In the insulator, we find the conduction band and the valence band. In this part, I would say that the energy level, which is, as we see in this video, is not really, is half or smaller than the forbidden gap in the insulators, because it have the same both properties, conduction property and the insulator property. In the semiconductor case, as we visualize the energy band, we would have two situational cases, and this the first one is low temperature. In the low temperature, and second one is the high temperature. In a high temperature, we would say that the high temperature, the more energy the electrons will gain, and will allow them to move from the valence band to the conduction band, leaving behind them holes. These holes is when the potentiometer is connected to it. It allows the holes and electrons to move around the material, causing it to move electric current. And in low temperature, the electron doesn't have enough energy to move from the valence band to the conduction band. And in this case, it have the insulator property. Between these two cases, the movement of the electrons move around, and this depends on the semiconductor part.
So, hello everyone. My name is Shangda. Now I'm going to introduce to you the details about the p-n junction. So let's start now.
When p-type and n-type silicon are placed in contact with one another, it forms a p-n junction at this junction. An interesting phenomenon occurs that is the foundation of the solid-state electronics. A basic p-n junction creates a diode that allows electricity to flow in one direction but not another. We can see in the diode that the n-type materials has free electrons and p-type materials have holes. Near the p-n junction, the electrons diffuse into the vacant holes in the p materials, cause a deposition zone. In addition, there leaves a small electrical imbalance inside the diode. Since the n region is missing some electrons, it has obtained a positive charge, and extra electrons that fill in the holes in the p region has given it a negative charge.
Now let's connect the diode to a power supply, a battery with a light and a current meter. That indicate current flow. The negative terminal of the battery is connected to the n-type silicon. We know that like charge repel, so the free electrons are pushed towards to the p-n junction. Similarly, the holes are repelled by the positive terminal of the battery. If the voltage pushing the electrons and holes are sufficient strength to overcome the depletion zone, the electric holes combine at the p-n junction and current passes through the diode. When the diode is Arranged this way with a power supply, it is said to be forward biased. In this example, the negative terminal attracts the positive hole in the p-type silicon, and the positive terminal of the battery attracts the free electrons in the n-type silicon. All the charge carriers are pulled away from the p-n junction. A solar cell is a p-n junction with a large surface area. The n-type materials is seen to allow light to pass through to the p-n junction. Light travels in packets of energy called photons. The generation of electric current happens inside the depletion zone of the p-n junction. The depletion zone, as explained previously with the diode, is the area around the p-n junction where the electrons from the n-type silicon has diffused into the hole of the p-type materials, where a fountain of light is observed by one of their atoms. In the n-type silicon, it will dislodge an electron, creating a free electron and a hole. The free electron and hole have sufficient energy to jump out of the depletion zone. If a wire is contact from the concealed n-type silicon to the anode p-type silicon, electrons will flow through the wire. The electron is attracted to the positive charge of the p-type materials and travels through the electrode load, creating a flow of the electric current. The hole created by the dislodged electron is attracted to the negative charge of the n-type materials and migrates to the back electrical contact. As the electron enters the p-type silicon from the back electrical contact, it combines with the hole, restoring the electrical neutrality.
Okay, so we have reached the final part, which is the conclusion part. I will explain about the conclusion and conclude all the have explained by Abdulaziz and Zhang. So what we have learned from the first video to this last video, we can earn something that we can use for our future, which is how energy band diagram works and semiconductor application of semiconductor in our life. So we can say that semiconductor is used to improvise our daily life in technology. So energy band diagram is occur in the semiconductor. I want to make a explanation where forbidden energy gap is same as energy band gap. So it's a different term that we use in the books and this video. So I don't want to make you all confused about